Hello, everyone. This is part 2 of chapter 9, which is on confidence intervals. Today, we're going to finish up what we were talking about last time, and then I'm going to go over different sample problems that will show up in homework and tests and things like that. And I'll show you how to solve them using your TI-83-84 calculator. And so that's what we're going to do today. All right. So the very first thing I'm going to do is share the screen with you. All right, we're good. And next thing we're going to do is go to that PowerPoint and just review a couple things with you. You remember last time we wanted to create a confidence interval for a population proportion. And this is the formula that was used for this, the general formula. So what did we do? We selected a sample, came up with our sample proportion, and that was our point estimate. And then we added and subtracted what's called the margin of error. This is this whole thing on the right here. The critical value times this thing, the square root here, which is the standard error for a sampling distribution of a sample proportion. Okay, so it's the point estimate plus or minus the margin of error. They call it a bound on the error estimation in the book. The term I use is margin of error. That's more common. Okay, so we used this example last time to determine a confidence interval. In this case here, it was a survey of 1,031 adult Americans. And out of that survey, 567 of them indicated they believe a college education is essential for success. So for this particular sample, the sample proportion is 567, the number of people who said it was essential for success, a college education, divided by 1,031 people who were asked the question. We divide those two numbers, we get 0.55, and that's the sample proportion. That's about 55%. Okay. What is a 95% confidence interval for this proportion? How do we create it? Well, we create it from our sample proportion. Before we actually use the procedure for creating a confidence interval, we have to meet certain conditions. Number one, if you remember this, for proportions only, that n times p hat has to be greater than or equal to 10, and n times 1 minus p hat has to be greater than or equal to 10. So when you multiply 1,031 times 0.55, you get 567. That's very much bigger than 10. And then when you multiply 1,031 times 0.45, you get 364, also much greater than 10. So we meet that condition. The other condition, of course, is that the sample size is much smaller than 10% of the population size, which it is in this case. And the third condition is that we got this sample from a random sample. In other words, we use some sort of random sample procedure, such as simple random sample or cluster random sample, stratified random sample, one of those. All right, so we met all the conditions. Now we can use the procedure. Now, since n times p hat and n times 1 minus p hat are both greater than or equal to 10, we can use the normal. We could say that the sampling distribution for p hat is approximately normal. And that's why we can use this z critical value here for our critical value. That's for a normal. All right, so p hat, which is our point estimate, plus or minus the margin of error. The margin of error is the z critical value times the square root thing here, which is the standard error. Plug in 0.55 for our p hat. We get all of these. The z critical value, if you remember, for a 95% confidence interval is 1.96. How did we get that number? We used inverse normal. We drew a little bit of a curve, right? We drew a curve. Let's see if I can actually make the highlighter. I don't know if that works or not. So it doesn't seem to be working for me right now. No, that's a laser pointer. I don't want a laser pointer. I want a pen, but it's not giving me the pen. Interestingly enough. All right. For some reason, it's not working today. And I think what I need to do is go back to, there we go. All right. So anyway, you draw your normal curve. The middle is going to be 95%. The rest is 5%. Half of it's on the left of the curve. If you can picture that, half of it's on the right of the curve. That's 2.5% on the left, 2.5% on the right. So when you do inverse normal, it's asking for the area to the left. That's 1 minus 0.025. That's your area to the left. And then your mean is 0, standard deviation of 1, because we're calculating the z. And we would get 1.96 for critical value. All right, so when you plug in all these numbers, you end up with this confidence interval. 0.521 is 0.55 minus the margin of error. 0.579 is 0.55 plus the margin of error. We did that last time. Okay. You wanted a 90% confidence interval. What would change, only thing that would change, is the z critical value. So you would draw a normal curve. The middle area is 90%. That leaves 10%. Half on the left, which is 5%. Half on the right, which is 5%. So therefore, when you do your inverse normal to find the z critical value, your area will be 1 minus 0.05. And when you calculate the critical value, you get 1.645. That's your z critical value. And therefore, interestingly, what happens here is that the interval becomes more narrow than for a smaller level of confidence. The interval becomes more narrow. For a larger level of confidence, which is 95% in this case, it becomes wider, the interval. Okay, 99% confidence interval, your critical value is 2.58 now, and it's even a wider interval. So this is the general rule. As your level of confidence increases, the length of your interval becomes wider. Okay, now this is the part we did not do last time, which is choosing a sample size. Typically, researchers, when they do want to do a survey, they have to determine ahead of time, before they actually do the survey, the number of people that they're going to survey. Now, do they do that sort of randomly? They just pick a number out of the air? Or is there some procedure of coming up with your sample size? Well, if you remember the margin of error, now we use E instead of B here, but that's okay. Just realize this is the margin of error for a population proportion. Notice this formula has N in it. So what we can do with this formula is we can square both sides and solve for N. And we end up with this formula. That is P times 1 minus P times the square of the ratio of 1.96 divided by B. Now, where did they come up with 1.96? That's the critical value for a 95% confidence interval. Obviously, if it was another type of confidence interval, another level of confidence, we would have a different number right here. So what do we need to know ahead of time to come up with our sample size? Well, we have to have an estimate for our population proportion, some estimate. We have to know the critical value. So in other words, we come up with our level of confidence. We determine that ahead of time. And we have to determine ahead of time how wide our interval is going to be. In other words, we have to determine our margin of error. Okay. So how do we come up with P? Well, P could be in a problem given where we have to find our minimum sample size. It may be given in the problem. They might say something like, from previous studies, P is estimated to be 0.3 or 0.4, whatever it might be. Or they may not mention it at all. So if there's no estimated P, what we're going to use for an estimate of P is 0.5. So make sure you write that down in your notes. If there's nothing mentioned in the problem about an estimated P, and we want to find the sample size, a minimum sample size for our survey, we're going to use 0.5 for P. And that means 1 minus 0.5 is also 0.5. In the problem, they will give you the margin of error. And the way they state it is they'll use the word within. They might say something like, I want my interval to be, my error to be within, and they might give you some percent, like 0.03% or something like that, or 3%, whatever. Okay. Anyway, we'll do an example just like it. All right, and I think there's one coming up right now. Let's just skip that. Here's the example. All right, it says, in spite of the potential safety hazards, some people would like to have an internet connection in their car. Determine the sample size required to estimate the proportion of adult Americans who would like an internet connection in the car to within 0.03. So that's your margin of error, 0.03, with 95% confidence. So 0.95 is your level of confidence. All right? So this is your bound. This is your margin of error. How do you find N? Now, there's nothing in the problem, nothing in this problem that's estimating P. So what do we use for P? 0.5. That's the key to doing this problem. Don't think that you can't do it because there's nothing here that mentions an estimate for P. Use 0.5. Or you use 1.96 because it's a 95% confidence interval. This is our critical value, 1.96. And what we're going to use for B here, and of course, if I was doing this on a test, I would use the letter E, but for margin of error. But anyway, you know this is the margin of error. What are we going to use? 0.03. We write it as a decimal here. So if they said to within 3%, you would convert it into decimal and put 0.03 here. All right. So 1.96 divided by 0.03, you square that. You multiply by 0.5 times 0.5, which is 0.25, and you get 1,067.111. Well, as you probably know, a sample size has to be a whole number. It can't be just a part of a person, right? 0.111 of a person. So what do? You just round up to the next whole number. Doesn't matter how small the decimal is. If N has a decimal in it, we round up to the next whole number. So the answer is 1,068 people. So what did we just find? We just found that if we wanted to determine the minimum number of people to interview for this survey, the minimum number, it would be 1,068, based on the idea that we want a 95% level of confidence, and we want our margin of error to be 0.03. Now, of course, we could survey more than 1,068 people, but this is the minimum amount. So we don't want to interview fewer than 1,068 people. All right. So what are we going to look at next? This is what we looked at last time, is confidence intervals for estimating a population mean, not a proportion, but a mean. All right, we're measuring something. We're finding the mean of those measurements. What's the general formula? Well, we have to, number one, use as our point estimate X bar. That's the sample mean from a random sample. Now, if you remember, for a population proportion, we had to make sure that N times P and N times 1 minus P was greater than or equal to 10. So we could use the normal distribution for the sampling distribution. In this case, when we estimate for a population mean, we use the central limit theorem. That is, the sample size has to be at least 30, or If we happen to know that the population is normally distributed, then it doesn't matter. The sample size doesn't have to be greater than 30, could be any sample size. But if we know nothing about the population mean or the population parameter that we're measuring, we must make sure that the sample size is at least 30. Now, in one case here, if we happen to know that the population standard deviation is known, then we're going to use this formula here for our confidence interval. That is, X bar is our point estimate, and we add and subtract our margin of error. Our margin of error, once again, is a Z critical value times the standard error. And what is the standard error for a sampling distribution of sample means? It's the population standard deviation divided by the square root of the sample size. So this is our standard error where we're estimating a population mean. Okay, there's our point estimate. There's our standard deviation statistic, which we call the standard error. And this is what the book calls the bound on the error of estimation. We're calling it a margin of error. All right. Now the question is sigma typically known? And the answer is no. Typically it's unknown. So when we do problems with this, we're going to typically deal with a situation where sigma is unknown. So we'll get to that in a second. All right. Now, let's look at an example where we're going to estimate what sigma is, in this case, 35. All right, it says cosmic radiation levels rise with increasing altitude, promoting researchers to consider how pilots and flight crews might be affected by increased exposure to cosmic radiation. Whew, a lot of words there. A study reported a mean annual cosmic radiation dose of 219 mRAMs. All right, this is a study, right? A study. So that means X bar, the sample mean, is 219. Suppose this mean is based on a random sample of 100 flight crew members, and the sample size is 100. Let sigma be 35 mRAMs. All right, so that is our estimate of the population standard deviation. All right, calculate and interpret a 95% confidence interval for the actual mean annual cosmic radiation exposure. Are the conditions met? It's a random sample. Yep. Number two, sample size greater than or equal to 30. Well, they don't mention that the population is normally distributed, so we have to make sure that n is at least 30. The answer is yes, it's 100. And is sigma known? Yes. In this case, it's no. So we're going to use this formula for our confidence interval. We're going to take X bar, add and subtract our margin of error. Z critical value, again, for a 95% confidence interval is 1.96. Our estimate of our population, standard deviation is 35, and we divide that by the square root of n, which in this case is 100. So when we calculate our margin of error and add and subtract that from 219, we get on our left endpoint 212.14, on our right endpoint 225.86. This 212.14 is 219 minus the margin of error, and this 225.86 is 219 plus this margin of error. Okay. Here's our interpretation. We are 95% confident that the actual mean annual cosmic radiation exposure for Xinjiang flight crew members is between 212.14 mREMs and 225.86 mREMs. All right, so there's an example of how to use this confidence interval for estimating a population mean when the population standard deviation is unknown. But as we said a minute ago, it's typically not known. We don't have an estimate for sigma. Okay. So what do we use? Well, remember in our study of probability, one of the last things I mentioned was the idea of the t-distribution. The t-distribution is a distribution which has a mean of 0, a standard deviation could be bigger than 1, and the parameter that we use for the t-distribution is called degrees of freedom. Degrees of freedom. Degrees of freedom is the sample size minus 1. And this is the actual calculation of t. All right, it's a standardized score. It's x bar minus the mean divided by the standard error, which notice here we don't use sigma anymore, we use S. What is S? It's the standard deviation for the sample that we've chosen. All right, so we have the x bar for that sample, and we also have the standard deviation S for the sample. And that's divided by the square root of n. So this S divided by the square root of n becomes our standard error. All right. Now, what's the important properties of t-distribution? It's bell-shaped and centered at 0. We had discussed this earlier. It looks like the standard normal. Each t-distribution is more spread out than the standard normal. Okay. As the number of degrees of freedom increases, the spread of the corresponding t-distribution decreases. All right. And here's the big takeaway. When the sample size gets large enough and the degrees of freedom gets large enough, eventually the t-distribution looks very much like the standard normal. Okay. Here's the general formula for confidence intervals for a situation when we want to estimate the population mean, but sigma, the population standard deviation, is unknown. This is typically the case. So what are the criteria? X bar comes from a random sample. Once again, we use the central limit theorem. If we know the population is normal, sampling distribution is automatically normal, but if we hold nothing about the population, then n, the sample size has to be at least 30. Sigma is unknown in this case, and we're going to use this formula now. So when sigma is unknown, we're going to use S in place of sigma in the standard error formula right here. This is the standard error. It's S divided by the square root of n. And instead of using the Z critical value, we're going to use the T critical value. And so I'm going to show you how that works in a minute. So best thing to do, of course. And what is that critical value? It's based on n degrees of freedom, which is n minus 1. So now it says to use tables here. We're going to use our calculator instead. All right. Now, this confidence interval is appropriate for small n only when the population distribution is approximately normal. All right, we already knew that. So let's actually do an example here. This is a funny kind of an example. It says chimps aren't charitable. It summarized the results of a research study published in the journal Nature. In this study, chimpanzees learned to use an apparatus that dispersed food when either of two ropes was pulled. When one of the ropes was pulled, only the chimp controlling the apparatus received food. When the other rope was pulled, food was dispensed both to the chimp controlling the apparatus and also a chimp in the adjoining cage. Whatever. The accompanying data represents a number of times out of 36 trials that each of the 7 chimps chose the option that would provide food to both chimps. In other words, they were charitable. All right? So these are the numbers, 23, 22, 21, 24, 19, 20, and 20. All right, those are the results for the 7 chimps. We're going to use, in this particular case, the mean. We're going to come up with a mean for these, for the sample. All right, so let's compute a 99% confidence interval for the mean number of charitable responses for the population of all chimps. So we're estimating this for, it says chimps, I guess chimpanzees, yeah. All right, anyway, they use 7 as the sample size here. Now, verify the conditions for the T interval are met. All right, so this is a random sample of 7 chimps. Yes, that's good. Now, since n is small, we need to verify if it is plausible that samples from a population is approximately normal. And one of the things they said to do here is use a normal probability plot. Now, we did not learn this in this course. It's more of something that's in statistics too. But this is called a normal probability plot. If it looks like it's reasonably like a straight line, then we consider it to be approximately normal. So just for all intents and purposes, let's just say that the population of these measurements is approximately normal. All right, so don't worry about that plot that we just saw. I'm not going to test you on that. All right. Anyway, if we took the sample average of those 7 chimps, we would get 21.29, and the sample standard deviation of 1.8. The degrees of freedom is n minus 1, which is 7 minus 1, which is equal to 6. So, what are we going to do? We're going to say our standard, our margin of error is going to be the t critical value times the sample standard deviation divided by the square root of the sample size. Now, we're given 1.8 as the standard, not given, but if we put these 7 numbers here into our calculator, and I think maybe we should do that, verify these numbers. I'm going to write down these 7 numbers. I think it would be useful to actually enter these numbers into our calculator. That's what we're going to do. Let's do that first. All right, and so we'll go to our calculator. So let's get to the calculator here. All right. So the first thing I'm going to do is go to stat and hit enter. And I notice that L1 and L2 are already taken, so I'm going to scroll over to L3. And you can do the same while we're doing this. You can enter those 7 numbers for the 7 chimps. All right. And to find the mean and standard deviation for L3, where our data is in, again, we're going to hit stat, scroll over to one variable statistics, hit enter, and we're going to use L3 here. So we'll do second 3, scroll down, hit enter, and there is our mean and standard deviation. So our mean is 21.286. If I round it to 3 decimal places, now a sample standard deviation is S here, so it's going to be 1.799. I guess we'll put 5. I'll maybe make it to 4 decimal places. Let's make it to 4 decimal places. All right. Okay, so there's where we find our, if we're given data, we can find our sample mean and sample standard deviation right here in one variable statistics. Let's go back to the slides. Okay. So what do? They rounded the mean and standard deviation to 2 decimal places. So this would become 21.29 for a mean and 1.80 for a standard deviation. So that's where they got the numbers from. All right. Now, where did they get the 3.71 from the t critical value? Now, if you remember, this was a 95% interval, I believe. Let's just go back. And, oh, they went a 99% interval. Oh, all right. 99% confidence interval. All right. So, where did they get the 3.71 from? Let's go back to our calculator. And we're going to use inverse t here. Now, for those of you who have the 83 calculator, I hopefully had programmed into your calculator a program right here, which would have been called inverse t. You would click that, or you would enter, you would go to inverse t, you would enter it once, and then enter it again, and then it would ask for area to the left. You would put that in. You would then you would enter, and then you would it would ask for the degrees of freedom. You would put that in, hit enter, and then it would give you your critical value. All right. Anyway, we're going to actually do the 83 version of this, or excuse me, 84 version of this. We're going to go down to inverse t. This is where everybody has the 84 calculator. Now, the area they're asking for is the area to the left. Now, for a 99% confidence interval, think about it. The area in the middle is 0.99. What's left? 1%, right? 0.01. Half of it's to the left, that's 0.005. Half of it's to the right, 0.005. That means the area to the left that we want here is 1 minus 0.005. All right? That's how we came up with the area. Degrees of freedom, there are 7. If the sample size is 7, we want to put 6 in here. Hit enter, and we get 3.7074. Okay, that's what we get for our Z critical value. If we go back to the, notice they use 3.71 here, which is rounded to 2 decimal places. Okay. Now, they did a lot of rounding here, so this is the interval they end up getting. 3.71 times 1.8 divided by the square root of 7. Notice you put 7 in here for your sample size. You put 1.80 for the standard deviation, sample standard deviation. And you calculate your margin of error. You add and subtract that from X bar, and you get 18.77 as your left endpoint, 23.81 on the right endpoint. Now, if you were doing this with your calculator, after you calculate your critical value, you can multiply this. So you can actually hit the multiplication key, so you don't have to do any rounding here. Just multiply this by the standard deviation. Now, if you remember, I didn't originally round it to 2 decimal places. I rounded 4 decimal places. So it was actually 1.7995 for the standard deviation. And then I divided by the square roots of 7. Hit enter. And that is our margin of error. Now, if you remember, I don't know if I showed this to you last time. I think I did. You can store the margin of error into an alpha character. So I'm going to hit store, hit alpha, go down, and I like the letter T, so I'm going to use 4 here, and it comes up with the T. Hit enter, and now this number 2.52 is stored in the letter T. This will just make it a lot simpler. Now, we've come up with a confidence interval. The left end of the confidence interval is going to be the sample mean, which when I figured it out, was 21.2851. I rounded to 4 decimal places, and I'm going to subtract T, because that's my margin of error. And there's my left end point. And then I'm going to say 21.2851, which is my mean. And I want to add T, alpha T. And there's my right end point. So if you wanted to round it at this point to 2 decimal places, you would have 18.76 on the left, 23.81 on the right. Go back to the slides. And pretty close to what they got. Why did they get 18.77 on the left? Because of rounding. The answer from your calculator is more accurate than the answer here. Okay, so some rounding error here, but it's very close to the answer we got with our calculator. All right, so that's how you figure out a confidence interval for a mean when we do not have an estimate of the population standard deviation. So what are we going to use? We're going to use the sample standard deviation instead for the standard error part of the formula. And then we're going to use T critical value instead of a Z critical value in the margin of error formula. Okay. All right, anyway, back to the slideshow. And then the interpretation is we're 99% confident that the mean number of charitable responses for the population of all chimps is between 18.77 and 23.81. Now, What if we wanted to have, just like we did for proportions, what if we wanted to find the minimum sample size for a study where we're estimating a population mean instead of a population standard, instead of a population proportion? Now, here's the key. We have to use, even if we don't necessarily know sigma, the population standard deviation, here's the margin of error formula right here, all right? Or 95% confidence interval. It's Z times sigma divided by the square root of n. We cannot use T here, and why? Because we're trying to estimate the sample size. We're trying to determine the minimum sample size. But S, or the critical value for a T is determined by the sample size, the degrees of freedom. So if you're trying to solve for it, you're going to have some trouble. So you have to come up with an estimate for sigma if you come up with a minimum sample size. All right, so we have to use this formula for the margin of error. You cannot use T and S, right? Because we don't know anything about the sample. So if we rearrange this formula and solve for n, we end up getting Z. Now they say 1.96, but remember this is Z critical value times sigma divided by, and remember I call it E, they call it B, the margin of error, and you square this ratio, you get your minimum sample size. So best thing to do is do an example. All right, so let's do this as an example. The financial aid office wishes to estimate the mean cost of textbooks per quarter for students at a particular university. The estimate to be useful, it should be within $20 of the true population mean. Now, see the word within? That gives you the clue that this $20 is your margin of error. How large a sample should be used to be 99% confident of achieving this level of accuracy? Well, C, the level of confidence is 0.95, and $20 is your margin of error. Now, unfortunately, there's nothing in this problem that tells you an estimate for the standard population standard deviation. That's a problem. So, what are you going to do? Well, the book, your textbook, if you read through chapter 9, what you will find out is that they came up with a sort of their own little procedure here for determining an estimate of sigma. What do they do in this case here? It says the financial aid office believes that the amount spent on books varies with most values between $150 and $550. So, come up with an estimate for sigma. What you do is you subtract those two numbers and divide it by 4. All right. This is sort of a fly by the boots. I guess I don't know if I'm saying the metaphor correctly, but anyway, it's basically some way of estimating this population standard deviation. So you take the range of values, right? You subtract the largest value minus the smallest value, that's the range, and you divide it by 4. All right, this is what the book recommends. And so an estimate of the population standard deviation is $100. All right. Well, let's use our formula. Now it's a 95% confidence interval that we want. So we're going to use 1.96 for a critical value. Our estimate of sigma is 100. And our desired margin of error is 20. When we multiply 1.96 times 100 and divide by 20 and square it, we get 96.04. Since we have a decimal here, we round up to the next whole number, and we get 97. All right, so this means that we have to, this is our minimum sample size, 97. We could have larger than 97 if we wanted to in our study, but definitely nothing less than 97 in our study. All right, and that's it. All right, so Anyway, what we're going to do next is we're going to do some examples from the book, and that'll be it for the day. So um, let's get to the textbook. All right. So where is the textbook? Here it is. And we're going to start on page 466. 466, and we're going to look at problem number 9.5, this one right here. All right, it says each person in a random sample of 20 students at a particular university was asked whether he or she is registered to vote. So they responded with R if they're registered, or with N if they're not registered. And here is the results of the 20 students. Use this data to estimate P, the proportion of all students at the university who are registered to vote. Well, out of the 20, if we counted the number of R's, we would end up with 14 R's here out of the 20. P, therefore, is equal to 14 divided by 20. Or excuse me, P hat is equal to 14 divided by 20. And the answer is 0.7. So that is our estimate. That is our P hat, our point estimate of the proportion of all students at this university who are registered to vote. Okay, so we used our sample data and came up with 14 divided by 20.7. Forgive me for this line here. I think the printer that I have here is basically needs a new cartridge, so I think that's why I'm putting this line. So you don't mind it. Doesn't bother me, but hopefully it doesn't bother you. All right, now next problem we're going to go to 9.8. Okay, so we'll go back to the book. Look at 9.8. It's on the next page. Yeah. A random sample of 12 four-year-old red pine trees were selected, and the diameter in inches of each tree's main stem was measured. And the resulting observations, those are the 12 diameters. Now, I changed the problem here. Instead of saying compute a point estimate of sigma, which we are not studying in this course, I want to find a point estimate of mu. All right, so just know that I'm asking a different question than what they're asking here. And so what do? Well, we have to put these 12 numbers into our calculator and then determine mu. All right, now, and that would give us our point estimate. All right, so let's go ahead and do that. And actually, I've already done that. I remember correctly. Basically in L1. L1. So those are the 12 numbers, I think, in L1. If I scroll down. Oops, I think we need to scroll over to L1. Scroll down. Yeah, those are the 12 numbers. 12 diameters, right? I think those are the 12 diameters. Let's go back to the problem quickly. I just want to double check that's true. Yeah, 11.3, 10.7, and so forth. Yep. So how do we find the mean, the sample mean? You all know how to do it. You just go to one variable statistics, put L1 in for our list. This second one, that's where our numbers are. Scroll down, hit enter. 11.9666. So that is our sample mean. If we go back to the solutions here, 11, we're rounding to 2 decimal places, 11.97 inches is our estimate of our, so this is our point estimate of the population mean, 11.97 inches. All right, so this is for a mean, this is a mean estimate, this is a proportion estimate, all right? So just want to make sure you understand the difference. Let's go to page 470. Now that was section 9.1. We're going to go to section 9.2. The textbook. We're going to go to the problems in the back, page 476. Let's go back to the book, page 476. And we're going to go to problem number 9.2. No, 9.14. I'm sorry, 9.14. This one right over here. The article about career expert provides do's and don'ts for job seekers. Okay. All right. So we have data from a survey of 2,667 hiring managers and human resource professionals. The article noted that many employers are using social networks to screen job applicants, and that this practice is becoming more common, like Indeed, right? Indeed is of the 2,667 people who participated in the survey, 1,200 of them indicated they are using social networking sites such as Facebook, MySpace, and LinkedIn to research job applicants, okay? So this is obviously a proportion problem, right? We have a count, 1,200. We have 2,667 people, sample size, and we're counting that there's 1,200 of them, of those 2,667, that use these sites for researching job applicants. Assume that the sample is representative of hiring managers and all hiring managers and human resource professionals. Construct and interpret a 95% confidence interval for the proportion of hiring managers and human resource professionals who use social networking sites. All right. Now, how do we do this problem? Well, we're estimating a population proportion in this case here. So the only thing we need is the sample size, right? And we need a sample proportion. Now, what is the sample proportion? 1,200 divided by 2,667. All right. So let's actually go to the problem here. Here's our proportion, and that comes out to 0.45. Our confidence level is 0.95. Now, what is our margin of error for proportions? We always use a Z for our critical value, never a T, always a Z. Here is the square root thing here. This is our standard error, or a proportion, sampling distribution for a proportion. Now, for 95%, we know that Z is 1.96. We know that P hat is 0.45. 1 minus P hat is 0.55. And our sample size is 2,667. So our margin of error is 0.0189. Okay. If we take P hat and add and subtract E, our margin of error. So P hat minus E is on the left endpoint. P hat plus E is on the right endpoint. We just plug in our numbers. P hat is 0.45. Our margin of error is 0.0189. We subtract these two numbers for the left endpoint. The right endpoint is 0.45, our sample proportion, plus the margin of error of 0.0189, and we get this number. So the confidence interval, the 95% confidence interval, is between 0.4311 and 0.4689. Okay. Let's look at the next example. On page 477, 9.17a. We'll go back to our book, go to page 477. And we go to 917a. So 917a is going to be, let's read through 917 first. If a hurricane was headed your way, you would evacuate. Would you evacuate? Well, that's what the study is all about. And so a survey research company states that 31% of people on a high-risk coast will refuse evacuation order. So immediately you look at this. This is the study of how many people? 5,046 people. This is the sample proportion, 0.31. Immediately you see that. Okay. So that's all we need. The sample size, 5,046, and the estimate of the proportion, 0.31. Now, remember, whenever we do this problem, we didn't do it for the last problem, but I'll mention it in this problem. We have to verify that we can use a normal distribution for the sampling distribution of sample proportions. Okay, so we should be able to do that, right? Because n times p is much, much larger than 10, and n times 1 minus p is much, much larger than 10. So we're good. Now, this is for a 98%. And actually, let's go back to the problem because I didn't say it. Let's look at A. Use this information to estimate the proportion of coastal residents who would evacuate using a 98% confidence interval. So this is an interval here that have not used before. So let's see how we do this problem. Well, we would make a little drawing here first. This is a normal curve, a standard normal curve. The middle is the 98%. So 0.98 is in the middle. 0.02 or 2% is left. 1%, half of it on the left, which is 1%, half on the right, which is 1%. So 0.01 is on the left, 0.01 is on the right. So when we figure out the critical value for a 98% confidence interval, again, we're going to use inverse norm. And notice the area to the left is 1 minus the area to the right. So 1 minus 0.01, comma 0, comma 1. We get this as our critical value. Now, we can leave that in our calculator and multiply that by the square root of 0.31, which is our point estimate for the proportion, times 1 minus 0.31, which is 0.69, divided by 5,046. All of this underneath that square root. And this, our margin of error becomes 0.015 with all these other things. Now, if we're using a calculator, we would store this in our calculator, and then we would say p hat minus 0.015. What's p hat again? 0.31. Okay, we get 0.295 on the left. The right end point is 0.31 plus 0.015. You get 0.325 on the right. Okay, and that is our 98% confidence interval or to estimate the population proportion. All right, so let's now go to page 479, 9.31. So we now go to 2 pages further along. We go to 31. Discussion of digital ethics appears in the article, this article. One question posed in the article is, what proportion of college students have used cell phones to cheat on an exam? Suppose you have been asked to estimate this proportion for students enrolled at a large university. So that means you have to do a study, right? So you have to determine ahead of time how many students should you include in the study. Well, you say to yourself, all right, I want my margin of error to be 0.02. And I want my level of confidence to be 95% or 0.95. So let's go to our, now there's nothing in here that estimates the proportion. Nothing about any previous study, nothing at all. So let's go now to our problem. Now, if you are not given any estimate for p hat, when you're trying to find a minimum sample size, what you must use is 0.5 for your estimate of p hat. So this is your margin of error formula. Critical value z times the square root of p hat times 1 minus p hat divided by n. Again, if you solve for n, you square both sides and solve for n, you end up with this formula. Now, it's a 95%, you want a 95% confidence interval, so you know that z is going to be 1.96. You know your bound, your margin of error to be 0.02. So you put 1.96 divided by 0.02, square it. And then your estimate for p hat is going to be 0.5 because you weren't given any other estimate. So p hat times 1 minus p hat. All right, and you end up with exactly, so in this case, there wasn't any decimal. You end up with exactly 2,401 as your minimum sample size. You don't have to round up in this case since the answer is an even number. Now, in 9.32 on the same page, let's look at 9.32. Next one down. All right, it says, in spite of the potential safety hazards, some people would like to have an internet connection in their car. A preliminary estimate, see, a preliminary survey of adult Americans has estimated this proportion to be somewhere around 0.3. All right, if they say something like preliminary survey, preliminary study, that's your p-hat that you're going to use in your minimum sample size problem, 0.3. All right, so they're giving you the estimate. All right, so they're asking here, and let's see if I can get this to move a little bit. Maybe I'll just minimize my picture. There we go. Part A is what you're going to be solving for in this problem. Use the given preliminary estimate to determine the sample size required to estimate the proportion of adult Americans who would like an internet connection in the car to within 0.02. That is our, when they say within, that's our margin of error, and that's our level of confidence, 0.95. So let's go to the problem. And notice that my estimate of p-hat is 0.3, my margin of error is 0.02, my level of confidence 0.95. Once again, since z is 1.96 for a level of confidence of 0.95, I'm going to put 1.96 for z. My margin of error is 0.02 in the denominator, and I'm going to multiply this, the square of this, by 0.3, which is p-hat, times 1 minus p-hat, which is 0.7. And notice in this case, I get 2016.84. And if I round, and I have to round it up to the next whole number, my minimum sample size is 2007, or 2007. All right, let's go to section 9.3. We have about 10 more minutes to go, and then we'll be done. And we're going to look at page 489, problem 9.36, so 489. All right. Here we go to problem number 36. All right. Here we have two intervals, two confidence intervals that are given. They come from the same data set, the same sample, computed using the same sample data. What does that mean? It means the sample mean is exactly the same for both of these intervals. By the way, how do you find the sample mean if you're given an interval? Well, you just take the average of the two endpoints. All right, you add the two endpoints together, divide by 2, you will get the sample mean. And if you notice in both cases here, if you do that, you'll get 115. So it is from the same sample data. Mu is, in this case, is a true average resonance frequency in hertz of all tennis rackets of a certain type. All right, doesn't matter what the words mean. Part A is, what is the value of the sample mean frequency? Well, I told you how to do it. You add the two endpoints and divide by 2, and you get 115. That's the answer to A. Pretty easy. Here's the interesting one, B. The confidence level for one of these intervals is 90%, and for the other, it is 99%. Which is which, and how can you tell? Well, if you remember the general rule that the larger the level of confidence there is, the wider the interval. So which of these intervals is wider? Well, it's the second one here, right? Because the lower limit is lower than the lower limit of this interval, and the upper limit is larger than the upper limit of this one. This is the wider interval. Now, you could also subtract these two numbers, and you get 1.8. Subtract these two numbers, you get 1.2. So this second interval is the wider interval. It must be the one with the higher level of confidence. So the second interval, 114.1 to 115.9, is the 99% interval. The one with the that's not as wide, this first one is the 90%. Okay, so that's something that I always ask on the final exam. I might give you a problem just like this. All right. All right, so let's look at the next problem. Next problem is, in the very next one, and 9.37. 9.37. Let's go to the text here. Samples of two different models of cars were selected, and the actual speed for each car was determined when the speedometer reaches 50 miles per hour. All right, samples of two different models. These are two separate samples now. The previous problem, these two intervals were for the same sample. These two intervals that you're looking at here are for two different samples. Why? Because this one was for one model of car, and this one was for another model of car. Two different samples, two different sample means. How do we know they're two different sample means? I'll show you in a minute. Well, if you add these two numbers up, you get 104, and divide by 2, you get 100. You get 57. That's not right. 52. So 52 is the average of these two numbers, right? So that is the sample mean. We add these two numbers up, we get 100. So 50 is the average here. So the average here is 52, and the average here is 50. Now, here's the thing. Assuming that the two sample standard deviations are equal, which confidence interval is based on the larger sample size? Okay, that's a little bit more complicated question. So let's go to the answer. Here's my answer, and then I'm going to prove it in this little section here. It says, all else being equal, the larger the sample size, the narrower the interval. Why? Well, that's what I'm going to prove in a second. So since 49.4 to 50.6 is more narrow than the other one, this must have the larger sample size, this interval. So the more narrow the interval, the larger the sample size, if everything else is the same confidence level, the same standard deviation. So let's just prove it here. So here are the two different samples. Let sample 1 be this interval. Let sample 2 be this interval. Now here's one of the other things that you should know about confidence interval. If you subtract the length of the interval, if you subtract the two numbers and get the length of the interval, it's always twice the margin of error. Because to get this number, we're subtracting from the mean, the margin of error, and over here we're adding the margin of error to the mean. So the difference between these two numbers here is twice the margin of error. So for sample number 1, the margin of error is going to be half of the difference between these two numbers, because the difference between these two numbers is twice the margin of error. To get the margin of error, we just subtract the two endpoints and divide by 2. We get 0.7. And we do the same thing for sample number 2. We subtract these two endpoints, divide by 2, and we get the margin of error is 0.6. Now for sample number 1, the margin of error is 0.7. That's going to be equal to Z for a 95% confidence interval. We know that's 1.96. We're being told that sigma for both of these intervals are going to be equal. So for this margin of error, this sigma, and then for this margin of error, it'll be the same sigma. So Z is the same in both margin of error formulas. Sigma is the same. The only difference is N. N has to be different. So what do? I do something a little fancy here. Scroll back up, I think all right. I solve for N for both of these formulas. And then I divide N1, the sample size for the first sample, and N2 is for the second one. I divide these two numbers, these two values, and what ends up happening, the Z's cancel, the sigmas cancel, and I end up getting 0.36 divided by 0.49, or 36 divided by 49, which, by the way, is less than 1. If I multiply both sides by n2, I say that n1 is equal to 36 divided by 49 times n2, which means n1 is less than n2. So if everything else is equal, all right, if everything else is equal, the larger the sample size, the more narrow the interval. Okay, and which of these intervals are more narrow? It's this one. We subtract these two values, it's 1.2. We subtract these two, it's 1.4. This is more narrow. This must have the higher sample size. So the bigger the sample size, more narrow the interval, and we always want a narrow interval. It gives us a better estimate of the population. Gives us a better estimate of the population need. All right. Hope that made some sense to you. All right, now we're going to go to page 489, 9.39a. So that's this one up here. All right. It says, in a study of academic procrastination, the authors of this paper reported that for a sample of 411 undergraduate students at mid-sized public universities preparing for a final exam in intro psych course, the mean time spent studying for the exam was 7.74 hours, and the standard deviation of study times was 3.4 hours. Now, here is we're going to be estimating population mean time study. Notice in this problem, there's no mention of sigma, but they do give you, they don't say it's a sample standard deviation, but they say the mean time spent studying for the exam was this, and the standard deviation was this. It comes from the study. This is the sample standard deviation. This is S. All right? So be clear, if they don't say sigma is equal to some number, if they give you a standard deviation, it's probably from the study. It is S. It's the sample standard deviation. So X bar is 7.74. S is 3.4. Construct a 95% confidence interval to estimate U, the mean time spent studying for the final exam. Okay. Let's go to our solution. Scroll down. Here's our mean. Here's our sample standard deviation. Sigma is unknown because they didn't mention it. C is 0.95. That's our level of confidence. Sample size is 411. Now, since we do not know this population standard deviation, we have to replace it with the sample standard deviation. We must use a T critical value. T critical value here. Okay? And we must use, for our standard error here, we must use S divided by the square root of n. The T critical value times the standard error with S in it is equal to the margin of error. Now, S is 3.40, N is 411, so we enter that in here. The degrees of freedom is 411 minus 1, which is 410. So for critical value, for T critical value, we use inverse T. People with your 83 calculators, you're going to use that program. For those with the 84 calculators, you're going to go to inverse T. What are you going to put inside for the area to the left? 1 minus 0.025, because the area in the middle is 0.95, and the area to the left must be 0.025. The area to the right is 0.025. So the area to the left of the critical value is 1 minus 0.025. The degrees of freedom is 410. You end up with this as your critical value, T critical value. When you multiply this by 3.40, divide by the square root of 411, you get this as your margin of error. In this particular case, I just approximated it to be 0.33. So for my 95% confidence interval, the left end of the interval is X bar minus the margin of error, 7.74 minus 0.33. The right end is 7.74 plus the margin of error, 0.33. And if I did the arithmetic correct, it's 7.41 on the left, 8.07 on the right. This is our 95% confidence interval. We must use a t-critical value. We must use S. Now, for 940A, which is on the same page, back 940, we're actually given a data set. So this is, what is this data set? Medical research has shown that repeated wrist extensions beyond 20 degrees increase the risk of wrist and hand injuries. I'm going to have to throw, excuse me for a minute. Sorry about that. Back to the problem. So each of 24 students at Cornell University, so 24 is our sample size, used a proposed new computer mouse design, and while using the mouse, each student's wrist extension was recorded. So that's what's recorded down here, the 24 wrist extensions, all right? The measures of wrist extension. So let's go actually down a little. I think we have to go to the next page. And what does Part A ask for? Use this data to estimate the mean wrist extension for people using the new mouse design using a 90% confidence interval. So what did we have to do? We had to enter the data into a list. And that's what's in L2 here. L2 was the 24 data points. Okay, so if we scroll over, I believe that's all of those data points, should be 24 of them. Yep, 24 data points. And if we go to, so that's an L2, so if we go to one variable statistics, hit enter, I'll put L2 in here, second 2. Scroll down, enter. Here's our mean, 25.917. I guess we can round it to 0.917. And here's the sample standard deviation. I'll say 1.954. Let's go back to the, all right. So here is the, now there was no mention in the problem of a population standard deviation. So we have to use our t-critical value in our calculation of the margin of error. Now, level of confidence, 0.90. Sample size 24, degrees of freedom 23. Here's our margin of error formula. Now, for a 90% confidence interval, we have the middle 90% of the curve. We use 90% in the middle of the curve. 10% is left, 5% on the left, 5% on the right. So the area to the left of the critical value is 1 minus 0.05, because the area to the right is 0.05. Degrees of freedom is 23. So that is our t-critical value, t.90. Inverse t, 1 minus 0.05, comma 23. We get this 1.7138 and so forth. We multiply that by 1.954, which is the sample standard deviation, divide by the square root of the sample size, which is 24, square root of 24. We're going to get this as our margin of error. In this particular problem, simply rounding the margin of error to 3 decimal places. And to find our 90% confidence interval, okay, I take my sample mean, 25.917, I subtract our margin of error, 0.684, and I get 25.233 on the left. On the right, if I take the sample mean and add the margin of error, that is, I take 25.917 and add 0.684, I get 26.601. So this is my 90% confidence interval. All right. The very last problem is a minimum sample size problem for a mean, for a study that will be estimating a mean. Let's get to, this is on page 492, problem 951. 492. And we go to number 51, 951. This one right here. The Bureau of Alcohol, Tobacco, and Firearms has been concerned about lead levels in California wines. In a previous testing of wine specimens, this is a previous study, lead levels range from 50 to 700 parts per billion. How many wine specimens should be tested if the Bureau of Alcohol, Tobacco, and Firearms wishes to estimate the true mean lead level for California wines to within 10 parts per billion? That is our margin of error. With 95% confidence, that's our confidence level. So they're giving us this range of values here, okay? What do we use this for? We use it to estimate the population standard deviation. We subtract these two numbers to give us the range of values. That's 700 minus 50 is 650, and we divide it by 4 to give us our estimate of our population standard deviation, right? Comes out to 162.5. So 95% confidence interval, we're going to use 1 point. Now we're going to use this formula, our critical value times sigma divided by E, the whole quantity squared. Use 1.96 for our critical value since it's a 95% confidence interval. We're going to use 162.5 as our estimate of the population standard deviation. And we're going to divide it by the margin of error that we would like, which is 10. And we square that whole thing, and we get 1,014.4225. We round it up. Our minimum sample size is 1,015. Okay, folks, that's a pretty long lecture. I am done. I think you probably are tired also of viewing this. So that is it for today. So I'm going to stop sharing now, and I wish you all a very nice rest of the week. I know there's holidays coming up on Friday. So for all of you who are celebrating these holidays, have a very nice holiday. Also over the weekend, and I will talk to you again on Monday. And what I'm going to be doing is going to be recording. This is obviously has been recorded. I will put this recording sometime this evening on Blackboard, just like I've done before. All right, and also the document, the problems for that I went over also will be posted on Blackboard. All right, so have a very good evening, and I will see you again soon.